In the present module, we shall introduce the idea of point estimation as a part of statistical inference. First, we shall discuss some historical perspective of the theory of estimation. Next, we shall discuss the concepts of observable random variables together with their sample space. The ideas of parameters and parameter space are also discussed in this connection. Some examples will be discussed. Finally, we shall discuss the terms relating to statistical estimation, say statistics, estimator and estimate. First, we shall introduce the idea of statistical inference. Statistical inference is the process of going from information gained from a sample to inferring about the population from which the sample is taken. Two aspects of statistical inference that will be taken up in this course are theory of statistical estimation and theory of testing of statistical hypothesis. First, we discuss the estimation theory. In an estimation problem, some features of the population in which an inquirer is interested in may be completely unknown. The inquirer will have to make a guess about the unknown feature completely on the basis of a random sample from the population. The problem of statistical estimation can be broadly classified into two categories. One is point estimation and the other is interval estimation. Now, we discuss some historical perspective of the theory of estimation. The problem of estimation arose in a very natural way in astronomy and geodesy in the first half of the 18th century. For example, in astronomy, determination of interplanetary distances, positions of planets, etc. were some important problems. In geodesy, determination of the parameters of the spheroidal shape of the earth was an important problem. It was known that the earth is almost spherical in shape except for some flatness near the poles. Observations on the measurement of the length of 1 degree of a certain meridian, say capital Y, were obtained, and the problem was to determine the parameters alpha and beta which specified the spheroid of the earth. Indirect measurements on alpha beta were given by the relation yj equals to alpha plus beta into xj, j running from 1 to up to n, where xj's are observations on some auxiliary variables and n is the number of observations. To estimate the parameters alpha and beta, the first attempt was done by Roger Voskowitz in the year 1757. He suggested that estimates of alpha and beta are to be determined such that the sum of positive and negative residuals or errors should be balanced. That is, summation over j from 1 to n yj minus alpha minus beta xj equals to 0. Subject to the first constraint, the sum of the absolute values of the errors, that is, summation over j from 1 to n modulus yj minus alpha minus beta xj is as small as possible. Laplace in the year 1789 gave a general algebraic algorithm for obtaining the estimates based on the above principles. The problem of latter solved by Gauss and Legendre for a slightly modified version of 1 using the method of least squares. For reference, you may go through the book by Stigler. The book is The History of Statistics. The errors or residuals are defined by epsilon j equals to yj minus alpha minus beta xj. Over the years, various researchers have attempted to provide a justified distributional assumption for the errors. Simpson in 1776 used the idea that errors are symmetrically uniformly distributed about 0. That is, the probability density of the epsilon j's is f epsilon equals to 0.5 into 1 by h. Epsilon lies between the interval minus h to plus h, where h greater than 0. Euler in 1778 proposed the arc of a parabolic curve given by f epsilon equals to 0.75 into 1 by h cube into h square minus epsilon square, where epsilon lies between the interval minus h to plus h for h greater than 0 as the PDF of the random errors. Laplace suggested what is now known as the bilateral or double exponential distribution, where the PDF of the error is f epsilon equals to half into 1 by h into e to the power minus mod epsilon divided by h for h greater than 0. Gauss proposed using the normal or Gaussian density with density f epsilon equals to 1 by h root 2 pi e to the power minus epsilon square divided by h square for h greater than 0 as the error distribution. Now we consider the background of the theory of point estimation. Let us consider a random experiment E. The outcome of the random experiment E is represented by an observable random variable, say x curl equals to x1, x2 up to xn. Here x is a vector with n elements x1, x2, xn. A particular realization of the vector x is denoted by small x vector, which is equals to small x1, small x2 up to small xn. The set of all possible realizations of the vector x is called the sample space, and it is denoted by script x. It is a subspace of r to the power n. We denote by capital F x vector, for which x belongs to script x, the distribution function of the vector x. In parametric point estimation, we assume that the functional form of f is known except perhaps for a certain number of parameters, say the theta vector, which is a d-dimensional vector with elements theta 1, theta 2 up to theta d. Theta is called the labeling parameter. The parameter theta varies over a set of values called the parameter space, and it is denoted by script theta. It is a subspace of r to the power d. The distribution function f can be looked upon as a function of the theta vector, and henceforth this dependence will be made explicit by writing f as f theta, where theta is a vector. If x vector admits a density, that is a PMF, probability mass function, or a PDF, probability density function, we will often replace the distribution function capital F by the density small f. We write the class of all distribution functions of the vector x as script f. This is the class of all capital F where theta belongs to script theta. The object of interest in estimation theory is the unknown parameter theta or some function g theta thereof. Now we consider some examples. Example 1. Suppose a coin, which may be fair or unfair, is tossed 50 times. The outcome of the jth toss can be described by a random variable xj such that xj is 1 or 0 according as the jth toss results in a head or a tail. The sample space can be described as script x equals to set of all x1, x2 up to x50, where each xj is equals to either 0 or 1 for all j. If theta denote the probability of a head in any toss, then script theta is equals to the interval 0, 1. The PMF of the vector x is given by small f theta x equals to product over j from 1 to 50 theta to the power xj into 1 minus theta whole to the power 1 minus xj, where x belongs to script x and theta belongs to script theta. We want to estimate the probability of a head theta or some function of it such as g theta equals to 1 minus theta, which represents the probability of a tail. Next we consider another example. Example 2. Suppose that 100 seeds of a certain flower were planted in 100 identical pots, one in each pot. Let xj equals to 1 or 0 according as whether the jth seed germinates or not. The data generated by this experiment is an ordered 100 tuple of zeros and ones and is a realization of the x vector, the components of xj being IID random variables with probability x1 equals to 1, this is equals to theta, and probability x1 equals to 0 is equals to 1 minus theta. The object of estimation is the probability of germination of each seed theta or a function of it such as g theta equals to 10 choose 8 theta to the power 8 into 1 minus theta whole square, which represents the probability that in a batch of 10 seeds exactly 8 germinate. Next we consider a famous example. In a path-breaking experiment, Rutherford et al. Observed 2608 time intervals of 7.5 seconds each and counted the number of time intervals capital NR in which exactly R alpha particles hit the counter. The data is displayed in the table. where there is a values of r starting from 0 up to greater than equals to 10, corresponding to each values of r there are nr values. The Poisson distribution with mean theta, where theta greater than 0, serve as a good model for the number of times a given event E occurs in a unit time interval. If xj denotes the number of alpha particles hitting the counter in the jth time interval, then x1, x2 up to x2608 are IID Poisson random variables with mean theta. Next, we consider another example. Consider the problem of determination of a physical constant such as the acceleration due to gravity g. G is estimated by the pendulum experiment. We observe x equals to 4 pi square L divided by capital T, where L is the length of the pendulum and T is the time required for a fixed number of oscillations. Due to uncontrollable factors such as the skill of the experimenter, the jth observation is xj, where xj is modeled as g plus epsilon j, where epsilon j's are random errors. Assuming epsilon j follows normal distribution with mean 0 and variance sigma square, then xj's are IID normal random variables with mean g and variance sigma square. Here theta curl is an ordered double, that is a vector with two elements g and sigma square, and we might want to estimate g or sigma square or both. We consider our last example. Suppose an experiment is conducted by measuring the length of lives in hours of n electric bulbs produced by a certain company. Let xj be the length of life for the jth sampled bulb. Then our sample space is the set of all n tuples small x1, x2 up to xn, where each xj is greater than equals to 0. If we assume that the distribution of each xj is exponential, then the joint PDF of the vector x is given by 1 by theta to the power n e to the power 1 by theta into summation over j from 1 to n xj, where x belongs to script x, theta belongs to script theta. We may want to estimate theta or any function of theta, say g theta equals to e to the power minus 60 by theta, which represents the probability that the lifetime of a bulb is at least 60 hours. Now we introduce the basic objective of our point estimation problem. The distribution of x vector is characterized by an unknown parameter theta, about which we only know that it lies in the parameter space script theta. For the sake of simplicity, we restrict our attention to the problem of estimation of some real valued function of theta, say g theta. Say for example, g theta equals to summation k from 1 to d theta k square. In point estimation, we try to guess the value of g theta on the basis of the observed realization x, small x, of the vector capital X. We try to put forward a particular statistic, that is a measurable function of the random sample x vector, say capital T equals to Tx, which would approximate g theta very closely. Mathematically, capital T is a measurable mapping from script x onto the image space of G, that is g theta is a subset of the real line. An observed value of t, say small t, is called a point estimate of g theta on the basis of the realized sample x. It is to be noted that a point estimate of g theta may vary from sample to sample. From example, if x and xi are two different realizations of the vector x, then t of small x may be not equals to t of xi. We close our discussion with an example. In our previous example 1, suppose we wish to estimate theta, then we may use the statistic capital T, which is the average values of the xj. This can be taken as an estimator for theta, as the xj's are zeros or ones. So t belongs to 0, 1, and hence t is an admissible estimate of theta. We have seen that the theory of estimation was originated from astronomy and geodesy problems. The basic object of estimation theory is to provide a statistic which would represent the unknown parameter theta very closely. But the problem is that for a particular parameter theta, there may be several estimators. So we require some criteria for selecting a good estimator. That will be discussed in our next module.